So the lecture today will be about the differentiability of monotone functions or functions of bounded variations. So I'll discuss the differentiability of monotone functions. Right? So if I have a function f defined on an interval ab and taking values in R, I will say that it's monotone increasing if I take x less or equal than y. This implies that fx is less or equal than f of y. And the first main theorem will say that if you have a monotone increasing function, then this function will be differentiable almost everywhere. Of course, I can replace here by increasing by decreasing, and here I just need to replace this inequality less or equal, then by a greater or equal, then to have a decreasing monotone functions. So this is a definition. And what I want to prove, as I said, is that if you have a monotone increasing function, this function will be differentiable almost everywhere. For that, I will define, say, the derivatives of f. So let me define d plus of f at some point x as the limit sup when h decreases to 0. So h takes positive values and it's decreasing to 0, and I'm taking the limit sup of x, f of x plus h minus fx divided by h. So that will be d plus, and d minus will be the same object, but where instead of taking the limit sup, I'll take the limit imp as h decreases to 0. And in the same way, I will define d plus, but with a plus below, of f of x as, well, the same object but taking the limit from the left. So this means that I'm taking the limit sup as h decreases to 0 of f of x minus f x minus h divided by h. So this is with a plus, and if I write d minus f, I mean that instead of taking the limit sup of this quantity, I will take the limit imp as h decreases to 0. So this is just a notation. These objects are all well defined. Observe that they are non-negative because f, it's monotone increasing. So these quantities are all non-negative, and therefore limit it's non-negative. And I will need these quantities in order to say what I mean by a function to be differentiable at one point, which is what I'm going to do now. So if f is a monotone increasing function, I will say that f is differentiable at x if all four quantities are equal. So if d plus f x, it's equal to d minus fx, which is equal to d plus fx, which is equal to d minus. So if these four quantities are equal, I will say that f is differentiable at x, and I will represent by f prime of x its derivative, which is d plus x. All right, and now, so let's say that f is defined on some interval ab, which can be equal to, so this can be also minus infinity plus infinity, I don't mind. And so let me define E as the set of points x in R. And here, well, if f is defined only in the interval ab, replace R by ab. So these are all the points x for which f is differentiable at x. So it's all the points x for which these four quantities are equal. Okay, so if you prefer, you can just replace this sentence, f differentiable at x, by these identities. And note that I'm not claiming that this set is measurable, right? I'm just defining this set. This is a subset of R. And what I would like to prove is that lambda of E complement, so I'm taking the points at which f is not differentiable, and what I would like to show is that this set has measure 0. So this is the first main result of this lecture, is to show that, well, this set has a complement whose outer Lebesgue measure, so remember that this is the outer Lebesgue measure, whose outer Lebesgue measure is equal to 0. So this is the statement of the first main theorem. Take a function f which is defined on an interval ab, which is monotone increasing, defined as by E the set of points x in AB for which these four derivatives are equal. So these are the sets of points x at which f is differentiable. And what we want to prove is that the outer Lebesgue measure of the complement of E is equal to 0. So this is the theorem I will prove now. So let's prove the theorem. The proof, again, it will be divided in several steps. So I just rewrote here the definition of the set E. And remember that we want to prove that the outer measure of the complement of E is equal to 0. Here note that I'm taking out A and B, well, because some of these derivatives are not defined at A or at B. So actually, let's define E in such a way. And, well, the E complement is the union. If x belongs to E complement, it means that, well, these inequalities, one of these identities does not hold. So what I claim is that you can E complement, it's included in the set of points x in AB, such that, let's say that d minus f of x is smaller than d plus f of x union. So you have, if one of these identities does not hold, you have four definitions of the derivative. You choose two of these four, and you have an inequality in one sense or the other. So actually here you have 2 times 4 choose 2 sets. And in order to show that the outer measure of E complement is equal to 0, it's enough to prove that the outer measure of each of these sets is equal to 0. So what I'm claiming is that, well, it is enough to prove that the outer measure of this set, the set of points x in AB, such that d minus f of x is smaller than d plus f of x, that this set has outer measure equal to 0. Okay, and the proof I will give for that set works exactly in the same way for the other sets. So what we need to prove is that, well, this set has measure 0. And now how to prove that this set has outer measure 0? What I claim is that, remark that this set, let me call it E1, that E1 it's equal to the union over all s smaller than t. S and t are rational numbers of the points of x in AB such that d minus of x it's smaller than s, which is smaller than t, which is smaller than d plus f of x. Okay, I claim that E1 it's exactly equal to that set, and that's very easy to show. Well, suppose that you belong to this set. This means that this derivative is smaller than that one. Well, then I can find two rational numbers which are greater than this one and smaller than that one, which means that this point x belongs to one of these sets, and therefore it belongs to the union. And in the same way, so that set, it's clearly contained in this one. On the other hand, if you take a point here in this union, it belongs to one of these sets. And if it belongs to one of these sets, this means that d minus is smaller than d plus, and therefore you belong to that set. So these two sets are equal. And since I have here a countable union, in order to show that the measure of that set, the outer measure of that set, is equal to 0, it's enough to show that the outer measure of each of these sets is equal to 0, because the outer measure of that set is smaller or equal than the sum of the outer measures. So if the outer measures are all equal to 0, this sum is 0, and therefore the outer measure of E1 is 0. So actually, what we will prove is that the outer measure of that set is equal to 0. So in the next blackboard, I will write down this set. I will recall what d minus is and d plus is, and then I will prove that the outer measure of that set is equal to 0. So this is the second step of the proof. Up to now, we reduce the proof to the proof that this set est, which is the set of points x in AB for which d minus f is smaller than s, which is smaller than t, which is smaller than d plus. So we reduce the proof to the proof that the outer measure of this set is equal to 0. And here I just copied what are the definitions of d minus and d plus. So we need to show that the outer measure of this set is equal to 0. So this set is bounded, and so fix epsilon positive. Okay. And we can find an open set. So G will be an open set which contains est and whose measure it's almost equal to the measure of est. So by definition, since the outer measure of est is finite, I can find an open set which contains est and whose measure is almost equal to the measure of est. So I can find this open set such that est is contained in G, and the measure of G, which is an open set, it's smaller than the outer measure of est plus epsilon. Okay. So since well, this set is bounded, I can always find an open set G with these two properties. And now let's start the proof. So I will use this inequality to construct a Vitalis covering of est. So now I'm going to construct a Vitalis covering of my set est. Well, how do I do that? Take a point x in est. If x belongs to est, its d minus derivative, it's bounded by s. The minus derivative is the limit inf as h tends to 0. So the limit inf of this quantity is smaller than s. This means that I can find, there exists, a sequence of hk converging to 0 such that fx minus fx minus hk it's smaller or equal than s times hk. Right? Well, the limit inf it's smaller than s. This means that, well, for infinite many values hk converging to 0, I can find I can find this hk for which this inequality holds. Okay? Well, these hk are all converging to 0. They are converging to 0. So now let's consider the interval x minus hk x. These will be the intervals of my Vitalis covering, but I don't want all of these intervals. I will just keep the small ones. And what do I mean by small? I mean the following. X belongs to est. Est is contained in G, and therefore x minus hk is converging to x, which belongs to an open set. This means that for k sufficiently large or h sufficiently small, these intervals will be all contained in G. So I'll keep from this sequence only those which are contained in G. Okay, so my Vitalis covering will be formed by all points x in St and all hk for which this inequality holds and for which this interval is contained in G. So my family I of sets will be formed by all intervals of the form x minus hk x, such that x belongs to est and fx minus fx minus hk, it's smaller than shk, and the interval x minus hk x, it's contained in G. Right? And what I claim is that this set I forms a Vitalis covering of my set est. Why is that so? Well, take a point z in est. Then I can find a family of intervals of the form z minus hk z. It's clear that these intervals all contain z. So z is a point in this interval, and the length of this interval, it's equal to hk. Hk are all strictly positive, and they are as small as one wish. So if I fix also a delta positive, for k sufficiently large, this interval has a length smaller than delta, and therefore this family of intervals form indeed a Vitalis covering of my set est. Okay? So this shows that this family I, it's a family which is a Vitalis covering of my set est. Now I will use the corollary of Vitalis' lemma, which we proved in the previous lecture, which asserts that for that given epsilon, I can find a finite family of disjoint intervals in this family, which essentially cover all the set est. So there exist intervals I1 up to IM. They belong to my family I. They are disjoint 2 by 2. So ij intersection ik is empty if j is different from k. And the outer measure of est minus the union of ij from 1 up to m, that this is smaller than epsilon. Okay. So this is the assertion of the corollary of Vitalis' lemma. Right? Since this is it's a Vitalis covering, for that fixed epsilon, I can find a finite subfamily of intervals which are disjoint 2 by 2, and for which the outer measure of the set minus the union it's smaller than epsilon. Now I have all the ingredients to conclude my proof. Let me just erase here the fact that it's a Vitalis covering to write my intervals. So these are intervals. They are all in this family, so they all can be written as x minus hx for x in EST. So let me write ij. Okay, ij it's one of these intervals. Ij can be written as xj minus hj xj, where xj it's a point in EST and xj and hj satisfy this inequality and this statement. And let me assume that when I'm writing that these intervals a1 up to am, they are ordered in the sense that I have here x1 minus h1, x1, and that x1 is smaller than x2 minus h2, x2, and so on, till the last one. So I'm assuming, and there is no loss of generality by assuming that, well, I1 is the leftmost one, I2 is the second leftmost one, and so on, and IM is the rightmost one. This will just simplify a bit the notation in the proof. Now, let's see what we can deduce from that inequality. I know that this inequality holds for all intervals. This means that if I sum j from 1 to m of fxj minus fxj minus hj, okay, since xj minus hj xj is an interval of my family I, they satisfy that inequality. So that difference, it's bounded by s times the length of the interval. So this is less or equal than s times the length. Okay. Well, now let's remind that these intervals are all disjoint 2 by 2. So this is the measure of the union of these intervals. So this is equal to s times the outer measure of the union of ij. Right? And now remind that all these intervals are contained in G. Right? All these unions, all these intervals are contained in G. This means that the union of these intervals is contained in G, and therefore the outer measure of the union is smaller than the outer measure of G. But the outer measure of G, it's bounded by construction of G by the outer measure of the set EST plus epsilon. So I can here write lambda plus epsilon, where I'm calling lambda this quantity here, just because I have no space to write lambda star of EST. So this is what we will need in the second step of the proof, is just the fact that this sum, it's bounded by s times lambda plus epsilon, where lambda is this quantity here. And keep in mind that these intervals I1, Im, they are all contained in G, and I assume that they are ordered. So, as I said, that I1 is the leftmost, I2 is the second leftmost, and so on, until Im it's the rightmost. This we will use in the third step of the proof. So I kept in this blackboard what we will need for the next step, which is step 3, I guess. So up to now we construct these intervals I1 up to IM. They are ordered. They are equal, ij is equal to xj minus hj xj. And we have proved that inequality, where I just remind you that lambda it's actually equal to the outer measure of EST. Okay. Now I will introduce a new set, and for the definition of this new set, I need to replace these closed intervals by open intervals. So I0j will be the interval xj minus hj xj. So these are just taking the same intervals, take the interior points of the intervals ij. And let me introduce a new set, B, which will be equal to EST intersection the union of these intervals, ij naught from j equal from 1 up to n. And what I claim is that the measure of B, it's almost equal to the measure of EST. So let me show to you what I claim. Well, EST, it's contained in EST intersection, which is B, or maybe let me write it, EST intersection the union EST minus okay, so this is actually an equality. I'm just writing down EST as the points which are in this set and the points which are not in this set. So this is an identity. But if now, instead of removing only the interior points, I remove everything, this set gets smaller. And, well, but actually these sets, so what I want to say is the following. This is an identity. Therefore, the outer measure of this set, it's less or equal than the outer measure of this set plus the outer measure of that set. This is my set B. And this set, it's contained in EST minus the all sets. Union, well, what's the difference between these and these? Well, here I removed the endpoints of the interval ij. Here I didn't. So it's certainly contained in these set. Remember that the endpoints are my points xj minus hj and xj. Okay. So the outer measure of that set, it's less or equal than the outer measure of this set, which is bounded by epsilon by construction of my sets ij, plus the outer measure of that set, but the outer measure of that set, it's equal to 0. So this is bounded by epsilon. And therefore, I have that the outer measure of B, it's larger than the outer measure of EST minus epsilon. So let me write this conclusion here, that the outer measure of B, it's larger than the outer measure of EST, which I'm calling lambda, minus epsilon. That will be important for what I need later. So let me erase this argument. And now let me construct a Vitalis covering of my set B. So I want to construct now a Vitalis covering of my set B. And the way I will do that, It's exactly the same way in which I obtained a Vitalis covering of my set EST. But now I'm going to use that inequality instead of the first one. So let's take a point y in B. Since y belongs to B, d plus f of y, which is given by that, it's larger than t. So this means that this limit sup, it's larger than t. If the limit sup is larger than t, this means that, well, I can find a sequence h converging to 0 for which this inequality holds. That means that there exists a sequence which I will represent by r converging to 0 for which f y plus rk minus f of y, it's larger or equal than t times rk. Right? Because the limit sup, it's larger than t. And this will be the intervals of my Vitalis covering of B. So let me call J the intervals of type y plus rk, such that y belongs to my set B, and for which rk is this sequence converging to 0. But I will not keep all rk, but only the small ones. Why the small ones? Because I will need an iter. And what do I mean by small? I mean the following. Y belongs to B. This means that Y, let me call this set the set H, which is an open set. So Y, if Y belongs to B, then Y belongs to my set H, which is open. This means that if Rk is sufficiently small, then the interval y plus Rk, it's contained in this open set H. And saying that, well, this open set H is actually the union of these intervals, which are the joint intervals, this means that actually this interval, it's contained in one of these open intervals. So I want to retain only these Rk for which this interval is contained in H. So I want Rk such that the interval y plus y plus Rk, it's contained in the union of ij 0. And just keep in mind that if you are contained in this union, it means that you are contained in one of these intervals. And then let me write down what I mean here. Well, I know that f of y plus Rk minus f of y, it's bounded below by t times Rk. Okay. So these are a family of intervals, which I'm calling J. And what I claim is that J forms a Vitalis covering of my set B. So let me prove that. So I claim that this family J, it's a Vitalis covering of my set B. And to prove that, take a point Z in B, right? Take a delta positive, and we need to find an interval which belongs to my family J, which contains Z and whose length is smaller than delta. Well, but that's very easy, because since Z belongs to B, Z belongs to the interval Z plus Rk. And what is Rk? Well, this is the sequence we obtained from the fact that this derivative is bigger than t. So there exists in this family a countable number of such intervals whose length is equal to rk, and rk is going to converging to 0. So the length of this interval, which is rk, is smaller than delta for all k large enough. So since rk is strictly positive, this proves that this family J is indeed a Vitalis covering of my set B. Now let's apply the corollary of the Vitalis covering lemma. J, it's a family of intervals which forms a Vitalis covering of B. Therefore, by the corollary of the Vitalis lemma, we can find a subfamily. So there exists a subfamily which I will call J1 up to Jn, such that the outer measure of B minus the union of J1 from up to n, it's smaller than epsilon. This is just the application of the corollary of Vitalis lemma. Since this is a family, for that given epsilon, we can find a finite subfamily, which I'm representing by J1 up to Jn, for which the outer measure of B minus this union, it's bounded by epsilon. And now let me show that what I claim is that, well, these intervals are the total length of these intervals, it's large. Why is that true? Well, because B, it's certainly equal to B intersection the union of J, k, from k equal to 1 up to m, union B minus these intervals. Okay. This means that the outer measure of B, it's less or equal than the outer measure of this set plus the outer measure of that set. So let me write it here. Well, the outer measure of this set it's contained in this union, so the outer measure of this set, it's contained in the outer measure of this set. These intervals J1, Jn, I didn't write them, but it follows from the Vitalis lemma, they are disjoint 2 by 2. So the total measure of this set, it's equal to the sum of the lengths of the intervals, n, and it's always n, I'm writing n. Right? So the outer measure of this set, it's bounded by the sum of these outer measure. The outer measure of this set, it's smaller than the outer measure of this set. And the outer measure of this set, it's bounded by the sum of the lengths of gk. Actually, I don't need to use the fact that they are disjoint. It's just an inequality I want. And on the other hand, well, we've seen that by construction of these intervals, the outer measure of this difference, it's bounded by epsilon. Okay? So this means that the total length of these intervals gk, it's larger or equal than the outer measure of B minus epsilon. But the outer measure of B, it's bounded below by lambda minus epsilon. This shows that the total length of these intervals, it's bounded by lambda minus 2 epsilon, where, remind, lambda, it's the outer measure of EST, right? So we used here, once again, the Vitalis covering lemma in order to get these intervals. as I said, these intervals are disjoint, 2 by 2, right? The outer measure is small, and from the fact that the outer measure of this set is small, we deduced that the total length of these intervals is bounded below by lambda minus 2 epsilon. So we have these intervals, they are disjoint, they essentially cover all the set B, and the total length is almost the outer measure of EST. So it's the outer measure of EST minus 2. It's bounded below by the outer measure of EST minus 2 epsilon. So let me erase what I just proved. Just keep the final result somewhere. So here we just show that if I take the union of all these intervals, gk, the total length is larger than lambda minus 2 epsilon. That will be needed later. So up to now, what did we do? We defined the set B this way. We obtained from this Vitalis covering a finite subfamily, which is disjoint 2 by 2, and which is essentially covering the set B. And what is important here is that all these intervals of my Vitalis covering are contained in one of these open intervals. So now let me give names to J1. So let me call Jk. Jk will be an interval which I will represent by yk plus rk. Okay. And again, I will assume that these intervals are ordered in the sense that J1 is the leftmost interval of this collection, J2 is the second leftmost, and so on until Jn, which is the rightmost. Now, in the argument, let's use this property of these intervals. So they are all contained. This means that the first interval, probably it's contained in the first interval. So y1 plus r1 should be the leftmost one, therefore it should be here. Then we have the second leftmost up to one interval here. Then we have an interval here, another here, maybe another here, and so on. But what is very important is that all these intervals j are contained in one of the big intervals I. This is by construction. And why is that important? Well, because now I will argue that the increment of f over the large interval, and by increment I mean the difference between f at x1 and f at x1 minus h1, so that this increment, it's larger than the sum of the increments over these small intervals, because f is monotone, right? Since f is monotone, its difference in these 2 points, it's larger than the difference in these 2 points, plus the difference in the second interval, plus the difference in the third interval, and so on. So if I want to write that precisely, I need to introduce a new notation, which may be heavy, but well, let me introduce it because I want to be very precise. So let me write, we are here working on the first interval. So instead of writing y1, let me write this interval as an upper subscript, a superscript, meaning that this y belongs to the first interval, to the interval I1. So that will be the interval y1, y11 plus r11. So this will be the first interval. And then I have here the last interval, which I will write as y1, saying that we are still on the first interval, and this is the last one, so let me call it n1, and y1 n1 plus r1 n1. Okay? So I'm giving a new notation for all intervals which are contained in I01, in the first of these intervals. And what I'm saying is that the total increment of my function f over this interval, it's larger than the sum of the increments because f it's monotone. So what I'm saying is that, well, f, so this is x1 minus f x1 minus h1. So this is the increment of f over this interval. But because f it's monotone, this increment has to be larger than the sum, or maybe let me write it here with a space, from I going from 1 up to n1 of the smaller increments, which is, this is f y1 I plus r1I minus f of y1I. Okay? So the increments over these small intervals are bounded by these increments because, well, the total increment is actually the sum of this increment plus this increment plus that increment plus that one plus that one. And all are positive, which means that we have that inequality. Okay? And this holds not only for that first interval, but for all intervals. So I wrote here the inequality for the first interval, but if I want to now generalize that, I will just replace 1 by an index, which let me call it j, and I will sum over j from 1 up to m, and I will say that this is larger than this increment j from 1 up to m, and here I have to replace 1 by j, so nj, this is j, j, and j. All right? Well, but what do we have on the right-hand side? On the right-hand side, what we are doing is that we are summing the increments over all intervals j1, j2, jn, right? What's appearing here, it's a new enumeration of these intervals j1 up to jn. This means that what's written on the right-hand side is actually exactly the same thing as writing k from 1 up to n, because there are n intervals, of f yk plus rk minus f yk. Okay? So what we proved is that this sum over the large intervals, the increments, the sum of the increments over the large intervals, it's bounded below by the sum of the increments over the smaller intervals. Okay? I hope you're convinced about that. So I will erase the step which led to that conclusion, and I have enough space to conclude the proof of the theorem, because now I will just recall that inequality. So I know that f yk plus rk minus f of yk, it's bounded below by t times rk. So this is bounded below by t times rk. But what is rk? Rk, just the length of gk. jk, right? And we proved that the length of jk, the total length of these intervals, it's bounded below by lambda minus 2 epsilon, so that this is bounded below by lambda t minus 2 epsilon. Okay? So now, let's see what we have. So let's read these inequalities. We have that lambda, which is multiplying t minus 2 epsilon. It's smaller than that, which is smaller than that, which is smaller than that. But here, we proved that this sum, it's bounded by that one. So, what is the conclusion of all that? The conclusion is that lambda t minus 2 epsilon, it's less than or equal to s times lambda plus epsilon, right? And this holds for any epsilon. Epsilon was a fixed parameter that we imposed at the beginning of the proof. So we can let epsilon to 0 to conclude that lambda times t, it's smaller than s times lambda. Well, but we know that s is strictly smaller than t. So for that inequality to hold, we need lambda to be 0. So this implies that lambda is actually equal to 0. And what is lambda? Well, lambda, it's the outer measure of EST. So that proves that the outer measure of EST is equal to 0. And this is exactly what we wanted to prove. So this completes the proof of the fact that any increasing monotone function is differentiable almost everywhere. So now let me prove a consequence, a lemma. The lemma states the following. Take a function f from AB to R and assume that it's monotone increasing. Then we know that f is differentiable almost everywhere. Let me represent by f prime its derivative. So f prime of x, it's the derivative of f at x. What I claim is that this function is Lebesgue measurable. It's non-negative. And moreover, the integral from a to b of f prime d lambda, it's less or equal than fb minus fa. So I'll prove that lemma, which is pretty easy, and then I'll give you an example in which this inequality is a strict inequality. Okay? So let's prove. Let me define a new function, fn, which at x it's equal to fx plus 1 over n minus fx, and this is divided by 1 over n. Okay? So this function fn, this sequence of function, it's measurable because, well, f, it's a measurable function. And this sequence, it's converging almost everywhere to f prime of x. Right? At all points at which f is differentiable, this ratio, it's converging to the derivative of the function. So this proves that, well, this function here, it's Lebesgue measurable because, well, it's the limit of a sequence of measurable functions, and we are taking sigma field, the Lebesgue sigma field, in which if a function, well, it's the limit of a sequence almost everywhere of sequence of measurable function, then it's measurable, right? Here it's important that our sigma algebra is complete. So we proved that f prime it's Lebesgue measurable. It's clearly non-negative because this sequence fn it's non-negative because f it's monotone increasing, so this difference it's positive. So that proves the first claim. Then it remains to show this inequality, but that's very easy. It follows from Fatou. Okay, so we have a sequence fn converging to f prime. By Fatou lemma, we know that the integral of f prime d lambda, it's bounded by the limit inf of the sequence fn. Okay. Of course, here I'm need to define f in a slightly larger interval because, well, fb plus 1 over n is not defined. So let's define f as fb for x larger than b. Right? Let me extend the definition of f. If it's still a monotone increasing function with that definition, and now this expression is well defined for x equal to b, and well, for any x in the interval ab. Fine, so let's replace now fn by its definition. So this is the limit inf of fn, but fn it's n times f at x plus 1 over n minus fx, and here I'm integrating with respect to the Lebesgue measure from a to b. But here we are integrating x1 plus n, so this is equal to the limit inf n times, well, I'm just translating the function f by 1 over n and integrating that function, so actually this is to integrate the function f from 1 plus 1 over n to b plus 1 over n of f d lambda, and I'm taking out the integral from a to b of f d lambda. And I'm taking the difference and multiplying that by n. So you see here I have the integral in the interval a plus 1 over n and b plus 1 over n, and here I'm removing the integral from a to b. So this is equal to the limit inf of n times, so what remains? Well, what remains when I take this difference, it's the integral from b to b plus 1 over n. And here, well, I'm integrating only starting from a 1 plus n, while here I'm integrating from a, so I have a minus a plus 1 over n f d lambda. Well, by definition, f it's equal to fb for all x larger than b, so this is constant equal to b, to f of b. The integral it's running over an interval of size 1 over n. I have n in front, so this is fb. And here, well, f it's increasing, so all these values are larger than f of a. So this expression here, it's larger than fa, and the interval is size 1 over n, but with the minus sign it becomes smaller or equal, so this is smaller or equal than fb minus fa, and this is exactly what's claimed by the lemma. So we proved the lemma, which states that f prime it's Lebesgue measurable, it's non-negative, and it satisfies this inequality. So now that the lemma is proved, let me give you a very simple example. Take your function f, which is defined in the interval ab. Okay. Let's take a point C here. Let's assume that a is constant, then it makes a jump from some value to another value, and then it remains constant until b. So that function is clearly increasing. Its derivative, it's defined on all points but on C, and it's equal to 0. So the left-hand side, it's equal to 0, while the right-hand side, it's equal to this, the size of this jump. So that's a strict inequality. This gives you an example in which this is indeed a strict inequality, and you have to keep that in mind. I mean, this example in mind to remember that you might have a strict inequality. So let me complete this lecture by extending the previous result to functions of bounded variation. So I'll define what a function of bounded variation is, and then I'll say some lemmas concerning that type of function. So let's assume that we have a function from AB to R, and let's take a partition. So I will represent by pi a partition of the interval AB. This means that I'll take a sequence of points t0 smaller than t1, smaller than tp, which will be equal to b. So this is a partition, and I will define the variation of the function f along the partition pi as the sum of the increments, of the absolute value of the increments, so fti plus 1 minus fti, and the sum will run from I equal to 0 up to p minus 1. So this is the variation of my function f along the partition pi. And there are two things. Maybe I want to take a partition which doesn't go up to b but up to some x. So in which case I will represent that by the variation of my function f along that partition pi, but the partition pi, it's a partition of the interval ax. So I'll just recall that in this way. So if I have a function f which is defined in an interval ab, but I consider a partition which ends at x, I will represent by this symbol the sum of the absolute value of the increments on this interval ax along this partition pi. And so this is one definition, and then I can also define the partition along the positive and the negative parts. So p f pi will be the sum of the increments, but I'm taking only the positive part of the increments. Okay, so remember that if I have a number a real number a in R, a plus represents the maximum between a and 0. Okay? So if this value is positive, it's equal to its value. If it's negative, I take it 0. So this is the positive increments, the sum of the positive increments, and in the same way, I have the sum of the negative increments, which now I will take the negative part, and a minus will be the maximum between minus a and 0. Okay, and of course, it's clear that if I sum these two, well, I get the total variation, which is given by that, right? So observation v f pi, it's equal to n f pi plus p f pi, right? And I have also note that a, it's equal to a plus minus a minus, and therefore I have that f last identity fb minus fa. So if I sum the negative and the positive variation, I get the total variation. If I take the difference, then I get the difference between fb and minus fa, right? So these are just notation and simple facts. For a given partition, I have the variation, the absolute variation, or the total variation of f along this partition. I have the positive variation and the negative variation. And these quantities are related through two formulas. The total variation, it's equal to the negative variation plus the positive variation. And the positive variation minus the negative variation, it's equal to the difference. And as I introduce this object, I can also add here ax to mean that I'm doing that pi, it's a partition over the interval ax and not ab, and therefore I get the positive variation on this interval, the negative variation in this interval along the partition P, and I have the same identities, where here instead of B I will get f of x minus f of a. So these are simple notations, but now what I will do, and maybe let me do that in this blackboard, is that I will define a new object which is, well, this is well defined for each partition, so let me take the supremum over all possible finite partitions. So let me define Vf as the supremum over all finite partition P of Vf pi, right? So now I'm taking just the supremum over all partitions, and I'm defining a new object which is the total variation of my function f, which I'm representing by V of f. And in the same way, I can define the total positive variation and the total negative variation just by taking the supremums. So let me define by Pf as the supremum over all partitions pi of Pf pi, and Nf equal supremum over all partition pi of F pi. So this is the positive variation of my function f in the interval ab, and this is the negative variation of my function f over the interval ab. And what I will prove in the next blackboard is that these two identities still hold for the total variations. And now I'm able to define what I mean by a bounded variation function. Well, a function will be called a bounded variation function if its total variation is finite. Okay, so I want you just to keep in mind the definition of the variation along a partition and the total variation, the positive variation along a partition and the total positive variation, the negative variation along a partition, and the total negative variation, because I will need that in the next blackboard. So, definition: a function f defined in AB to R is of bounded variation if Vf is finite. So now we know what a function of bounded variation is, and my claim is the following: take f defined in AB, assume that f is of bounded variation, okay. Then what I want to say is the two things which were the obvious for fixed partition, so that the variation of f along total variation of f is the positive variation plus the negative variation, and that fb minus fa it's equal to pf minus nf. So I'll prove the second one, and you'll see that the proof of the first one is actually exactly the same. So I leave the first one as an exercise, but it's actually exactly the same as the proof of the second one. So I'm assuming that f it's of bounded variation. Okay. So the positive variation, it's smaller. By definition, the positive variation is smaller than the total variation, and the negative variation is smaller than the total variation. Not from this equation, just from the definition of positive, negative, and total variation. So this means that Pf is finite and Nf is finite. Well, what does it mean that Pf is finite? Pf, it's a supremum over partitions. So since it's finite, I can find a partition which is almost equal to the positive variation, it's almost equal to the total positive variation. What do I mean? I mean that there exists a partition P1. So P1, I'll just write it for you. So this is A, which is equal to T0 smaller than T1 smaller than Tp, which is equal to Q. There exists this partition, if I fix epsilon, such that, well, the positive variation of f along pi, well, this is certainly smaller or equal than the total positive variation, because that's a supremum. But I can find one, and I'm calling that one pi 1, which almost attains this total positive variation. Okay? And it's clear, because the total negative variation is finite, that the same is true for the negative variation. But maybe it's a different partition. So let me call pi 2 a second finite partition, which almost attains the negative variation. So I just rewrite here that the negative variation of f along the partition pi 2, it's bounded by the negative variation of f, because that one is a supremum, and since it's finite, we can find one which almost reaches that supremum, so which is larger than the negative variation minus epsilon. So from these two inequalities, now observe the following fact. This is not Q, it's B. Now let me take the union of these two partitions, and let me call that pi. So pi, it's the partition P1 union P2. So I'm just taking the union of these two partitions. I get a new partition. Maybe some of these points are equal, but maybe some are different. And what happens if I compare the positive variation of f along pi 1 with the positive variation of f along pi? Well, pi has more points. So by convexity, well, by the fact that if you take a plus b and the positive part, that this is bounded by the positive part of a plus the positive part of b. So I ask you to check that inequality, the same inequality with minus in places of pluses, that it follows from this inequality that if you increase the partition, you increase the variation because of that. So this new partition pi, which is the union of the two partitions, also satisfies this inequality, because you are increasing the positive variation, you are increasing the negative variation. It's still bounded by the total positive or the total negative variation, and it's bounded below by that one, which is bounded by. So I can erase here pi 1, I can erase here the 2, and keep the inequality for that partition, which is the union. And now, well, remember that if I take the difference between these, the positive variation and the negative variation, I get FB minus FA. This was the previous blackboard. So it follows from these two inequalities that P F pi minus N F pi. Now this is bounded, so I'm taking here, I'm multiplying this inequality by minus 1, and I'm summing. When I'm multiplying that by minus 1, and I'm summing, I get here minus NF, and here minus NF plus epsilon. So this is bounded above by pi f minus NF plus epsilon, and it's bounded below by pi f minus NF minus epsilon. Right? And this, by the previous blackboard, it's exactly equal to FB minus FA. So we have that FB minus FA, it's bounded by this expression, bounded above, bounded below by that one. So that proves that FB minus FA it's bounded by Pf minus Nf plus epsilon and bounded by Pf minus Nf minus epsilon. And since this holds for any epsilon, we have proved this identity, right? And as I said, you have the second identity. The first identity is proved exactly in the same way, so that you just, instead of subtracting, you sum and you get the first identity. So I will, let me erase this blackboard to complete an argument. Now I want to look at this identity, but instead of observing it so I want to repeat this, look again at this identity, but instead of looking it at B, I'll look it at X, so as a function of X. Right? So let me take F, which is defined in AB, but instead of looking at partitions on AB, I'll look at partition on AX, and I'll get that Fx minus Fa, it's equal to Pf Ax minus Nf Ax. Okay, so this is the total positive variation of f in the interval Ax, and this is the total variation, negative variation of f along the interval Ax. And we have this identity, which is just the one we had before, but for the interval Ax instead of the interval AB. Well, but you see, this is an increasing function, right? The positive variation of f in the interval Ax increases as x increases. And the same thing here. This is also an increasing function in terms of x. Therefore, what we proved is that if f is a function of bounded variation, I can write f as the difference of two monotone increasing functions. Okay, so what we proved is that any function of bounded variation can be written as the difference of two monotone non-increasing functions. And what do we know about these functions? Well, we know that this function is differentiable almost everywhere. That function is differentiable almost everywhere. So from this identity, we conclude that any function of bounded variation is differentiable almost everywhere. So let me write that. So this is a corollary, if you want, is that if f is of bounded variation, then f is differentiable almost everywhere. Okay. And this is the last result of this lecture. What I didn't prove is that this is increasing in x and this is increasing x, but that's I leave it to you to show. It's very easy because, well, the variation can only increase if you increase the size, the length of the interval. So we stop here, and in the next lecture I'll start discussing properties of the derivative of a function which is monotone increasing.